Exercise 2.1 takes a look at log scales. The first thing we need to understand is just scales. Usually when we're dealing with normal numbers, we use the linear scale. So, for example, 0, 10, 20, 30, 40, 50. What you notice is each interval that we're going up by is being added by 10. And if we were to go back down the scale, we would subtract by 10. With log scales, instead of adding and subtracting to go up and down the scale or left and right on the scale, we multiply by 10. Okay, so, or divide by 10 for that matter. For further maths, we only deal with log base 10. So that's why we only multiply or divide by 10, nothing else. Here we have a little scale comparison. So at the top here, we've got 1, 10, 100, 1,000, 10,000, 100,000. These are your normal numbers, just showing you how quickly the numbers will go up. In between, we've got power numbers, and then at the very bottom, we've got the log equivalent. So log base 10, 1 is equivalent to 10. Log base 10, 2 is equivalent to 100. Log base 10, 3 is equivalent to 1,000, so on and so forth. Now, we can also extend the line to the left, and then what you notice is our powers become negative, and our log would also become negative, because if you take a look at the 1 here, it's equivalent to 10 to the power of 1. The log 2 is equivalent to 10 to the power of 2. Log 3 is equivalent to 10 to the power of 3, and so on and so forth. So essentially they represent the power on a normal number that's base 10. Okay, so that's where that log base 10 comes from. That's sort of besides the point. So what are log scales used for? They deal with data sets with extremely large ranges. Okay, so things like an earthquake, you might have tiny little earthquakes you might not even feel. But then on the Richter scale, you might have really large, 4.2 earthquakes, which can, I guess, rumble over buildings and other human infrastructure. So data sets with large ranges is ultimately what log scale's purpose is built for. And an example is the Richter scale, where earthquakes get larger and larger quite exponentially. So here's an example. What we have to do is copy the log base 10 scale, which is down below, and mark where the number 50 is on the normal number line, because we're given a normal number line here. But, well, not normal number line, just normal numbers as intervals on this number line. So the first thing we need to recognize is this top line are your stock standard numbers. Down below, we need to write down the log equivalent. So 1 on the normal number line as a logarithm is, for base 10 logarithm, is 0. 10 on the normal number line is 1 as a log 10 base 10 equivalent, so on and so forth. So get your CAS out. What you need to do is go into your scratch pad, press Control, and then the button 10 to the power of X, which is right next to 1, to get this interface, log, and then you got a little square with a brackets to fill in. What you fill in is the highlighted information. So you know the base is 10, so you type in 10 in the square box, and you know the value we're looking for on the scale is 50. So you would input 50 in the brackets. Once you've inputted that, press enter and you get 1.7. So what does this 1.7 mean? This 1.7 is on the log equivalent scale. Now, right between 1 and 2, we've got 1.5. So 1.7 would just be sort of closer to 2, right? So if we were to draw a line from there, that would be roughly this point there. Okay, and that's how you do the normal number to log equivalent conversion. Let me know if you have any difficulties with exercise 2.1, but that's all there is to log base 10. Thanks, everyone.